Last class we were on chapter 5, slide 16, I guess. But I'm just recapping. So, here there's a question that I mentioned in class. So, if we are trying to find the hypothesis for a difference between the average traffic flow on Friday 6th and Friday 13th, right? So our reference point is Friday 6th and 13th. So if the hypothesis is to find the difference, so the appropriate one would be number C, because if there is no difference, then the traffic flow would be 0, and if there is difference, then it can be either positive or it could be negative, right? So it can be either positive or it can be negative, right? So this would be the ideal hypothesis for to find the average hypothesis. Okay, so let's look at the conditions. So we are told to assume that cases are independent. So these are all the CLT conditions, right? So if you guys remember, these are the CLT, similar to the CLT conditions. So we are told to assume that cases are independent and there shouldn't be that much skewness, right? If you recall that there shouldn't be that much skewness. So the sample distribution does not appear to be extremely skewed. So this is the key point, right, that I was talking about. But it is very difficult to assess with such a small sample size. So it's difficult with a small sample size. So we might want to think whether we would expect the population distribution to be skewed or not, and probably not. It should be equally likely to have days with lower than average traffic and higher than average traffic. So this could be the case that that in some days the traffic could be higher and in some days it could be lower, right? So distribution is not skewed in some sense, and we do not know the sigma, and n is too small to assume S is reliable estimate for the sigma, right? So S is the reliable estimate for the sigma. Okay, so we need to care about the conditions, right? So what do we do when the sample size is small? So what do you do? So let's review. So what purpose does a large sample serve? Okay, it should be serve, not this one. So okay, as long as the observations are independent, so we have to care if it's independent, and as long as the population distribution is not skewed, a large sample would ensure sampling distribution of the mean is nearly normal. Okay, this is the keyword, and the estimate of the standard error is reliable, which is S over root n, right? So if you recall, the standard error is S over root n, right? So this is standard error. So normality condition, CLT, which states that sampling distributions will be nearly normal, hold true for any sample size as long as the population is nearly normal. So this condition is true, right? So as long as it's nearly normal. So we have seen that in the last chapter, basically we still need these CLT conditions, right? For inference, it's ideal we should have like a CLT, right? So let's look at this third point, that we should exercise caution when verifying the normality for small samples. Okay, it is important to not only examine the data but also think about where the data is coming from. For example, would I expect this distribution to be symmetric, right? And am I confident that outliers are rare? So if there are outliers which are not rare, if a lot of outliers in the sample set, it's not going to give us an efficient estimate, right? So we should care about this point, that there shouldn't be any outliers. Okay, so we have to be confident about that. Okay, and in the last class we also talked about the t distribution, right? So if you remember or recall, t distribution, let's say this is like a standard normal. T distribution is slightly, sorry, the graph is slightly, okay, so the t distribution have fatter tails, okay, roughly fatter tails, so their tails are fatter than a normal distribution, right? So when the population standard deviation is unknown, so when we don't know the standard deviation, the uncertainty of the standard error estimate is addressed by using a new distribution. Okay, then we use the t distribution when we don't know the population standard deviation, right? Then we use t distribution. Okay, so the distribution also has a bell shape, but its tails are thicker, right? I have shown you guys the tails are thicker than our normal. So if a normal, let's say if I draw like this, t distribution tails are thicker, so it starts little thick. Okay, therefore observations are more likely to fall beyond 2 standard deviation from the mean than under normal distribution. So this is one of the properties of t distribution, right? Yeah, here's a graph. See, for t distribution is the blue one, right? And the blue one, if you can see, the tails are a little bit thicker than the normal, right? So I hope it's helping you visualize. I'm using my stylus pen. So these extra thick tails are helpful for resolving our problem with a less reliable estimate, the standard error. Okay, so the standard error is a little bit less reliable estimate, right? As you can see. Okay, so the t distribution, some properties again I'll talk. It's always centered at 0, like a normal standard distribution, and has a single parameter, the degrees of freedom, right? Look, one thing is that as the degrees of freedom increases, it approaches normal. Okay, so they have a degree of freedom. The higher the degree of freedom, it approaches normal. Okay, so this could be like a conceptual question, and it is always centered at 0. Okay, this is roughly not very smooth. If I draw it again, see, it will center around 0, right? So you need to know that it's centered around 0, right? Okay, so here's a question: what happens to the shape of the t distribution as degree of freedom increases? I have already said it approaches normal, right? So this thing would approach normal, right? So here's like the back to the Friday the 13th. So they have collected the Friday 13th of in July, in September. So they have the actual like difference between 6th and 13th. So these are the differences, if you can see, right? Okay, so finding the t stat, there is a formula for the t stat. It's the point estimate minus the null value over the standard error, right? So this is only for a small sample mean when n is actually less than 50. Okay, and the degree of freedom, we always say it's n minus 1. Okay, so point estimate, the difference is like 1836. So let's go back to the previous slide. 1836. Okay, so let's say they just found the difference between 6 and 13, that's 1836. So if we go there, the point estimate, let's say the difference of the traffic on 13th and 6th is 1836. Let's say this is the difference. So we know the point estimate. the null value is, we assume the null to be 0, right? So that's the null, that there is no difference. Okay, null value always we assume it's a 0. And the standard error, we have to use the formula, right? So it's the standard error difference over root n, and root n here is 10. So this is just an example. We got the standard error 372. So the t-stat would be the point estimate minus the null, which I told you that the null by default is 0 if nothing is specified, and we found the standard error. So we found the t-stat. All right, so once we found the t-stat, all right, and we also calculated the degree of freedom. Okay, here when we are calculating the t-stat, you always need to observe the degree of freedom. Why? I'm going to tell you now. Because you know, when the degree of freedom increases, it approaches normal, as I have discussed right previously. So let's see. So we have to use the t-table to find the p-value. Okay, so we can use this link, right? And I will show you how to use the t-table. Okay, so let's look at the t-table, right? Degree of freedom is approximately 9, right? And what's the t-value is 4.94. okay, so we have to find from here the 4.94. all right, so when t is 4.94, let's look at it. Okay, okay, so if we just go back, so 4.94, let's assume that these values pretty close to 4.94, right? And in fact it's at say 9 degree of freedom. This is approximately 3.25, so 4 would be somewhere around here, right? 4 point something. That would be even lower. For one tail it may be like 0.02 significance level. Okay, let me use my it's like 0.02. let's say for two tail it's 0.05, right? So it is very significant, okay, even at the 5% level. So what's the conclusion of the hypothesis test? That it provides evidence of a difference between traffic flow on 6th, oops, all right, let me just 6th and 13th. all right, so we need to find, see, when we were looking at the normal table, there were no, like, degree of freedom over there. We could easily get it, but since in t-stat it's a two-tail test, and we always have to look at the degree of freedom, and 4 would be somewhere around here, as I have said. And see, at 3.25 it's 5% significance level at one tail and 10% significance at two tail, right? So our value is 4, so it's even more significant. So it's not even 5%, maybe like 2.5% of one tail, and maybe for two tail it's 5%. okay, so I will give you guys the t table and the normal table. So in the class on Wednesday, I'll give you guys example how to solve it. all right, so we did find a difference between the Friday 6th and 13th, but it would be interesting to find what exactly this difference is, and similarly we can use a confidence interval to estimate this difference, right? And the formula for a confidence interval for a small sample mean is point estimate plus minus ME, right? And ME is always calculated as the product of the critical value and standard error, right? Critical value and standard error. What's the 95% critical value, right? Remember in the last class when we were calculating the confidence interval, it was point estimate plus minus 2 times standard error, right? And I said actually 2 is roughly equivalent to 1.96, right? So it's almost like a 5% level. So similarly, ME we calculate critical value times standard error. So critical value for 95% is 1.96, if you guys recall, right? For the 95% confidence. For 90% in class I said it's 1.645. For 80% it's 1.28, right? But these are the critical values for normal table, right? These are not for t tables, it's only for normal table. But if n is large, when n is large or the degree of freedom is large, like when n is roughly 90, the t table will behave like a normal table. So it behaves like a normal table, right? Is that clear to everyone? Okay. So here they have used point estimate plus t times standard error, and previously for normal table we had point estimate then plus minus z times standard error, right? If you guys recall, right? This was for the normal table, and this is actually for the t table, right? Okay. So finding the critical value of t, we have already kind of seen that. So let's say the n is 10. When n is 10, degree of freedom is n minus 1. Always it's n minus 1. Okay, so we always subtract 1. So degree of freedom is 9, right? And if we want the two-tail probability of 0.05, so two-tail 0.05 is, oops, two-tail 0.05 is here, and it's here. So we have calculated that it would be, if you guys let's see that, it would be 2.26. Okay, so if I ask two tail, and if I say that at 5% level, or 5% level means the p-value is 5%, so two tail is 5%. We know the degree of freedom is 9 because there are 10 observations, so this would be our critical value, right? So you guys should be familiar to find the critical values for this, right? So it's pretty straightforward in that sense. So let's do an example. Okay, which of the following is correct, is the correct calculation of a 95% confidence interval for the difference between traffic flow between Friday 6th and Friday 13th, right? So we know the difference. So this is actually our point estimate, right? This is our point estimate, PE. This is the standard difference. We have n, we have standard error, right? So first thing first, we need to find the 95% confidence interval. For the 95% confidence interval for t value is 2.26, right? We just calculated before, and point estimate is 1836, right? So 1836, the formula, if we rewrite the formula, it's point estimate plus minus t value times the standard error, right? They have calculated the standard error for us, right? So it would be 1836 is the point estimate, plus minus t value is 2.26, and the standard error is 372. Oops. Right? 372. So it would be answer C. Right? Sorry, not answer C, but it's a positive number. Sorry about the mistake. It's answer number B, right? Because C has a negative, so I didn't see the negative, but B, it would be the answer, right? Is that correct? And if we tell you guys to find two-tail 90% confidence interval, let's go back to the t-stat. So 90% mean for total it will be 0.10, right? 0.10 would be the 90%. So in that case, if degree of freedom is 9, that means 1.83 would be the value, right, for a 90%. So this would be for a 90% confidence interval, right? Right. So interpreting the confidence interval. So which of the following is the best interpretation for the confidence interval we calculated? Uh, so we are 95 confident that on Friday 13 there are 995 to 2677 fewer cars on the road than Friday 6th on average, right? So this would be the best interpretation for the confidence interval we just calculated. Okay, so I hope this is clear for you guys, and I will give you some examples in class on Wednesday so you guys can practice, and we will also do some homework. But keep in mind, this is not going to be in midterm 1, right? So does the conclusion from the hypothesis test agree with the findings of the confidence interval? All right. Yes. The hypothesis test found a significant difference, and we have seen, because it's, the p-value is small, so we reject the null, right? And the null, we reject the null, and so it is a significant value, right? So the null said that there is no difference, right? Null said no difference, but that's not true, right? We have seen that because we rejected the null, right? Because the p-value was small, right? P-value was less than 0.05, right? It's similar to chapter 4. Do you think the findings of this study suggest that people believe Friday 13th is a day of bad luck? Well, no, this is just an observational study. We have just observed a significant difference between the number of cars. Okay, it's nothing to do with the people's belief. All right, so don't just think that Friday the 13th it's a bad day and that's why people are driving less. That's not maybe that's not true. All right, it's just an observational study. All right, so let's see. So this is the formula for the standard error, right? Most of you guys know that. And when actually the sigma is unknown, right? Then only we use the t distribution. If it is known, we usually use normal, right? When sigma known, then we use normal. All right. Conditions is again the the CLT conditions. It has to be the independence of observation. It can't be skewed that much, so no extreme skew. And when we construct the hypothesis test, this is the formula that we are going to use it for that. All right. So this is the case we should see. And for confidence interval, we use this formula. Right. I hope that's also pretty clear for you guys. Okay. Right. So now let's talk about paired data. So what's a paired data, right? So from this example, 200 observations were randomly sampled from the high school. So we have 200 observations from the high school. The same students took a reading and a writing test, and their scores are shown below. So it's in pairs, like the same student have a reading score and a writing score. Something like the SATs that you guys have taken, before taking admission to before taking admission, you have to take your SATs, right? So those are the paired observations. Like you observe a reading score, you also observe a writing score, right? At a first glance, does there appear to be a difference between the average reading and the writing score? We see that from this example, the writing score average is slightly higher. So the average is actually that black dotted line, right? If you see from our sample, so people in general get a higher score in the writing section than the reading section. Okay, just from these observation. Okay, so the same students took a reading and writing test, and their scores are shown below. Right, are the reading and writing scores of each student independent of each other? They are not independent, right, of each other, because it's the same person that's giving the writing test as well as the reading test, right? One who is proficient in let's say in English would have a higher writing score and as well as a higher reading score, most likely, right? So they are not independent, right? Not independent, no. Okay, so let's analyze the paired data. So when two sets of observation have special correspondence, that means when they're not independent, we call that as paired, right? So this is the critical thing. Okay, so I can ask like what's paired. So the definition is here. And to analyze the paired data, it is often useful to look at the difference in the outcomes. Okay, so the difference is reading score and the writing score, right? The scores are different, so that's the difference. And it is important that we always subtract using a consistent order. Okay, so what do they mean by the consistent order is that when you're finding the difference, it should be always reading minus writing. Okay, so you do it for the first observation, and then you can't say that okay, for the second observation I'll find the difference is writing minus reading. Okay, it has to be consistent, always reading minus writing. Okay, you can't say okay, I did it for the first 10 observation reading and writing, for the next 10 I will do writing minus reading. This is not consistent. You have to follow a consistent order, all right, or else we can't analyze. Okay, the thing we can't analyze properly. So don't make this mistake. And in fact, in lab classes, like in our lessons in Stata, the computer actually helps us to maintain a consistent order, right? So when we are using the computer, like a statistical software like Stata, we don't have to use we don't have to worry about the consistency because the computer does it for us. So but when you are doing it manually, make sure you are doing it properly. All right. So let's see. Right. So I will stop here today. We have covered roughly about 50 slides today, and I hope this would help you guys, right? So go through the lecture. I have actually covered from slide 8 to slide 67, right? About 60 slides. Make sure you watch the video once. If you don't understand, you can watch it twice. Okay, so if you go through them slowly, it will help you. I will post the YouTube link, and the good advantage of YouTube is you can set the speed. Okay, so if you think that I'm talking too fast, on YouTube you can select the speed and you can slow it down, or if you think I'm talking too slowly, you can speed it up. All right, so thank you class, see you on Wednesday, and I hope you guys are doing the homework properly, and I hope you'll watch this video. Okay, thank you, have a nice day, bye bye.